My name is Navid Madani. I'm going to present to you our paper called Domain-Specific Question Answering over Knowledge Graphs using Logical Programming Languages and LLMs. So, our work focuses on the task of knowledge graph question answering, in which we have a knowledge graph and corresponding questions that can be answered using that knowledge graph by traversing the graph from one node to the other. So we know that one of the primary focuses of knowledge graph question answering is to bridge the gap between human language and a structured knowledge representation. And we have seen recently that large language models are really powerful natural language understanding tools. And also, logical programming languages are so powerful in representing knowledge and querying knowledge. So we ask if we can equip LLMs with logical programming languages to tackle the task of knowledge graph question answering. We take the MetaQA dataset, which is a dataset containing around 300,000 end question entries, which can be answered given a graph, knowledge graph, which is on movie domain. So for example, here we have a question: what are the genres of movies written by Louis Melis? And we can reach the answer by taking the Louis Melis as an entity in the graph and traversing the graph until we reach the answer entity, which is which is crime. So another characteristic of this dataset is that each of the questions are also annotated with the path that we can take to reach from the question entity to the answer entity. So we use these paths in our work to translate each question to a Prolog query. So the first stage of the work for us is to build the knowledge graph in Prolog. So what we do is that we take each of the triples in the knowledge graph, for example, the departed, has genre, crime, and we just translate it to a predicate like has genre, the departed, crime, which also preserves the natural language characteristics of the question. Of the triple. So the next stage is to translate each of the questions to a Prolog query using a sequence-to-sequence model. So we can use any encoder-decoder model here. If we use T5 in this work to translate each question to a query, so we just remove the entity from the question and replace it with ENT, and then we just ask the language model to translate the representation of the question as a predicate. So we also restrict this work to domain specific because we need to translate each of the edges to one predicate, which also preserves the natural language characteristics of that edge. So that's why we only work on a specific domain in this work. So after training this model, we can take any question and translate it to a query, Prolog query, and run it over the knowledge graph and get all of the answers along with the traces from the question entity to the answer entities. So we observe that doing that not only gives us 100% accuracy on the test set of the MetaQA dataset, but also we see the sample efficiency of this neurosymbolic approach. We see that given only 1,000 samples, which is less than 1% of the training dataset, we can train a T5 model which can be used to answer all of the questions in the test dataset of the MetaQA dataset. So as a conclusion, we can see that in the case of domain-specific knowledge graphs, which edges are easily translatable to natural language and are limited and restricted, we can easily propose a neurosymbolic approach to combine LLMs with logical programming languages and tackle the knowledge graph question answering on this domain. Our code and all of the trained models are all available and open source on the GitHub, and please reach out if you had any questions. On the GitHub page, you can also find all of the pre-trained models. You can train your models on scratch on Google Colab, and you can also serve and visualize what your model does on the code that we provide. Thank you for listening.